So looking at section 5.2. 5.2 starts off with the general power rule, or the general power rule for integration. And what this is really telling us is very particular here. It's going to take some time to understand this, so we're going to take a few minutes to actually read out some problems and kind of mull it over through example. Remember back to the chain rule. If we had, let's say something like x squared plus 3x to the 1/2 power. If we had something like this and we wanted to take the derivative, we would start by saying, let's declare a u as an interior function, right? So we're going to have an f of u is equal to y, and a g of x is equal to u. In our case, the interior function here is going to be x squared plus 3x. And the exterior function is just going to be u to the 1/2 power. Now, the derivative of this thing, we know from past lectures, is found using the chain rule. That's d f du times du dx, right? Or another way of writing it is dy. That was the more common way we had to write it, right? We said this is called the chain rule, blah, 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 blah. Well, in this case, when we go and solve all of this, we're going to have d dx of x squared plus 3x raised to the 1/2 power. The derivative of u to the 1/2 with respect to u is going to be what? (1/2 u to the negative 1/2 power, right? Times the derivative of u with respect to x. So let me write this in a cool color coordinated way. Times the derivative of du dx, that is 2x plus 3, to give us 1/2. So we just said u is equal to x squared plus 3x, the negative 1/2 power, times 2x plus 3. So all of this put together it's going to look like this. D dx of x squared plus 3x raised to the 1/2 is equal to 1/2 times the fraction, the radical in the denominator x squared plus 3x, and the polynomial 2x plus 3 in the numerator. What's it going to look like, right? Now, let's say you didn't know this. And I said, integrate this thing. That's what this general power rule for integration allows us to do. It allows us to say, how do we undo the chain rule? And this idea of u to the n du dx multiplied by dx coming out to be u to the n du, what it's telling you is if you can identify part of your function that is the derivative of another part raised to a power, you can imagine this thing as being du dx. What's that derivative, right? I mean, what's that integral? Set that equal to u, and set the interior of u to the n to u and integrate with respect to u. That's a quagmire of a thing to say and to even think about. So let's see it. All right. In this first example, A, we've got the integral of 3 times 3x minus 1 raised to the 4th integrated with respect to x. But hey, notice, if we were to take the derivative of that interior of 3x minus 1, it's going to come out to be 3, right? So with that in mind, let's set u equal to 3x minus 1. Then we can rewrite this as du dx is equal to 3. And say that the integral of u to the n times du dx is what we've got integrated with respect to x, right? And here, just notice that n is equal to 4, right? That's what we're doing. But this is equal to the integral of u to the n integrated with respect to u. So why don't we replace everything we've got going on here? This tells us that du dx is equal to, or my mistake, du dx times dx is equal to 3 dx. We're going to replace that with du. We're just going to write du right now. And we already said u is equal to 3x minus 1. So now we're going to come back to our original equation and rewrite it using du and u. Is everybody cool with that? When we do that, that tells us that 3 times 3x minus 1 raised to the 4th dx, that can be rewritten as the integral of u to the 4th du. And that thing we can solve. That thing is equal to 1 over 5 u to the 5th plus a constant. And our final answer, we just have to substitute u back in. Is everybody cool with this? So what we are saying here is, let's start by noticing we've got something raised to a power. We can think of this as u. And hey, what do you know? The derivative of u with respect to x, that happens to sit outside, right? So du dx can be replaced with just du. And this 3x minus 1, it can be replaced with just u. So we can integrate u to the fourth, integrated with respect to u. And that's how we get this. Does that make sense? Yeah. Now, as another example, here we've got something raised to the first power, and its derivative happens to sit outside, right? So we've got u to the first and du dx times dx. So we can rewrite du dx times dx as du. We can rewrite this interior as u raised to the first power and integrate. When we do, get that. Now, jumping to the original 4 problems, let's look at C really quick. In C, we're told we've got 3x squared times x to the third minus 2, all raised to the 1/2 power, integrated with respect to x. Now notice really quick, if we say this interior thing is equal to u, then what this tells us is that du dx is equal to 3x squared, and that's it. Well, that happens to show up right here. So what we have is that the integral 3x squared times x cubed minus 2 raised to the 1/2 dx, this thing is equal to let me try to keep this color coordinated. Three x squared x cubed minus 2 1/2 dx is equal to du dx u raised to the 1/2 times dx, right? But we can rewrite this as u to the 1/2 du dx times dx. And it's not exactly true to say it this way, but we can kind of intuitively think of it this way. These differentials are, in a sense, it's not exactly true, but in a sense, cancel each other out. So our final differential will look like the integral of u to the 1/2 integrated with respect to du. Well, that we can do pretty easily. That happens to be equal to, anybody? So what?
Nothing, I'm just writing, so I can hear the question.
What's the integral of u to the 1/2 equal to?
U to the 1/2. Or u is,
It would be 2/3 u to the 3/2, right? Plus a constant. But hey, wait a minute. We just said u is equal to x cubed minus 2. So this is actually equal to 2 over 3 x cubed minus 2 raised to the 3 over 2 plus a constant. So this is just chain rule in reverse. The same logic is going to apply here as what we used with the chain rule. And it all starts off by making a couple observations. In this particular case, we started off by making an observation that the interior of our radical, its derivative happens to sit outside the radical. So if we were to say this is u, then this would be du dx. And from there, we're able to set up a set of rules that lets us more easily integrate this. It's reverse chain rule. Now, really quickly, what about d? How would d work? Well, d, we would say that this is u, right? And all of that's u. So then du dx would be negative 4x, right? Which we happen to have in the numerator here. So this is du dx divided by u squared times dx. And we can set up our chain rule for that. Folks at home, do we follow?
Yes.
I'm assuming this is a yes.
Great.
Awesome.
Yes.
Dope. So jumping now and comparing our solution to C. Just looking really quickly at what they have versus what we have. It's the exact same, right? And the process starts by identifying what this u is going to be. Here, we used u to be what's underneath the radical. Then we said, cool, we got du dx outside, and we used reverse chain rule to work everything out. In the last example, we would do much the same. We would say, look, this is u. Well, if that's the case, then du dx, according to this, would just be negative 4x. And that's what we got over here. That's what's in our numerator. So we have u to the negative second times du dx integrated with respect to x. And that let us solve the rest of it. So what about when we multiply and divide by a constant? How would we go about this thing? Let's start by observing that here, things aren't going to come out exactly as we want them to come out. There's a reason why. We've got the integral of x times 3 minus 4x squared raised to the second power integrated with respect to x. Well, I think I want to use this interior as u. So u would be equal to 3 minus 4x squared, which would give us then that du dx is equal to negative 8x. Well, I don't have negative 8x here. But I do have a u. What I have is x. So if I were to multiply by -8 and divide by -8, I would get the same value, right? So really quickly, let's just make that observation. The integral of x times 3 minus 4x squared, that quantity squared, dx, that is equal to the integral of -1/8 times -8 times x times 3 minus 4x squared, that quantity squared, integrated with respect to x. Now, hold on. I've got du dx now. So what this means then is that this thing, this x, it is equal to -1/8 times du dx. Agreed?
Yeah.
Right? Because we can just replace this with du dx. When we do, we're just left over with that -1/8. So all this together, tells us that x, the integration of x times the quantity 3 minus 4x squared, that quantity squared dx, it can be rewritten as the integral of 1/8, the negative of that, times du dx, u squared dx. Well, I can bring out that -1/8, and I can rearrange everything to get this thing comes out to be -1/8, the integral of u squared du dx, integrating with respect to dx. Well, general power rule, or reverse chain rule, as I keep calling it, tells us that this is equal to -1/8 u squared du. That I can solve. That I can solve pretty quick and easily, actually. This comes out to be -1/8. The integral of u squared with respect to u is going to be 1/3 u to the third, right? Plus a constant. 1/3 u to the third plus a constant. Or -1/8, 16, 24 u to the third plus a constant. So substituting u back in now, our answer is going to be -1/24, 3 minus 4x squared, that quantity cubed, plus a constant. Now let's check our work. The first thing we do is we define what u is going to be. Then we say, all right, cool, taking the derivative of that, we have -8. But I don't have -8 here, but I can inject it by multiplying by 1. I can force that -8 to show up if I multiply by a properly chosen 1, right? That's what we did right here. We just multiplied by 1. Then we said, cool, that allowed us to pull out du dx. And what was left over was the negative 1/8. So with all of that in mind, we're able to rewrite this original integral like this. We've got our du dx. We found a negative 1/8 hanging out, right? We rewrote this term as u squared, or that factor rather, as u squared. And we said, well, once we pull out that negative 1/8, we can rewrite this integrand, this integral, as u squared integrated with respect to u. Well, this I can calculate, and then I can multiply by negative 1/8. That's how we got to here, right? So cool, simplifying it and substituting u back in, we get our answer. And when we compare what we've done to what they've done, they pulled out that negative 1/8, just like what we did. Then they used reverse chain rule and substituted the u back in automatically and simplified it to get the exact same answer. Now, a point on this, just because it looks like you can use the chain rule doesn't mean you can. This is a case where this process fails. And it fails because you can't force an x in here. You could, but x can't be 0 then, which causes a fail case. Because this is not equal to this. The reason why is because when x is equal to 0, this thing doesn't have an answer. And you also can't bring out that 1/x. Because pulling out the value only works for constants. And x is not a constant here, right? So this leads to a fail case. Instead, what we would do here is we'd say, all right, well, let's expand this out. Let's first FOIL this, then multiply by -8. Then we can integrate. And that's what we do here. We FOIL out this term, then we multiply by -8, which makes sense because we would have 3 times 3, that's 9, times -8, that's -72. And we know that's where that term comes from. And then similarly here, 16 times 8 is times that 8 will be -128. So everything looks like it shakes out, right? And that's what they're doing. They're saying FOIL this, multiply by -8, then integrate. Just because it might look like the general power rule or the reverse chain rule doesn't necessarily mean it always will. You can't make a variable show up, but you can make a constant show up. So as another example, what about this problem? This one looks like a mess, right? But we would start by saying x cubed plus 1, that's equal to u. If that's equal to u, then du dx is going to be 3x squared. So I've got 7x squared. So I need to pull out something to make this work, right? What would we pull out here?
It's 3x squared, we can make it 7x squared.
How would we turn, well, let me rewrite it this way. Let me actually write it on the board and follow us and walk us through this problem. First, we've got the integral of 7x times the quantity x cubed plus 1 raised to the 1/2 integrated with respect to x. we're going to say let u be equal to x cubed plus 1. Then du dx is equal to 3x squared. Well, I have a 7x. 7x squared, my mistake. I miswrote that. I could, however, break that 7x squared up, right? 7x squared is equal to 7 over 3 times 3x squared, isn't it? But wait, there's more. I feel like Shambhala up here right now. So if that's the case, then 7x squared, that's really equal to 7 over 3 times du dx. Well, now we can start rewriting things. Now we've got the integral of 7x squared times the quantity x cubed plus 1 raised to the 1/2 power, integrated with respect to x. That is equal to the integral of 7 over 3 du dx times u raised to the 1/2 times dx, right? Now, this we can rewrite. This we can rewrite as pulling out that 7 over 3, the integral of u to the 1/2 times du dx integrated with respect to dx. And this is equal to the integral 7 over 3 times u to the 1/2 integrated with respect to d. Well, this integration I know how to do. 7 over 3, the integral of u to the 1/2 du. This is going to come out to be 7 over 3 times 2 over 3, u to the 3 over 2, all that plus a constant. So this is going to become 14 over 9 times u to the 3 over 2 plus c. And when we substitute u back in, we get 14 over 9 x cubed plus 1, all raised to the 3/2 plus a constant. And checking our answer, that is exactly what happened, right? Notice here they say just multiply and divide by 3. And the idea is the same, right? You're just multiplying by 1 and then rearranging the terms to force that 3 here. Same exact thing as what I've done over here. And the answer is the same. Yay, we have not broken math yet.
Just for
I mean, that's kind of what this is going to feel like, right? Up to this point, I've been showing how to use substitution of variables to solve these problems. And that's because personally, I find this the easiest way to do these. They would prefer that you just stick with the general substitution rule, I mean, the general power rule. The general power rule of integration, I should say, is what up to this point they have presented in the way they do the work. But the way I presented it on the board is using substitution. So for that reason, we're going to breeze through this pretty quick. So to start off with in this problem, we've got 1 minus 3x, that quantity raised to the 1/2 power. So what's u going to be?
U is 1 minus 3x.
Okay, what's du dx going to be? Just the derivative of this interior, right?
So we just make it 3.
Yeah, just be -3. So we would start by saying, let's substitute u. So we've got u inside. Now, du dx, that's -3. So we're going to have to multiply by -3 and divide by -3. Because that's just the same as multiplying by 1. That gives us a du dx. And we can rewrite du dx times dx as just du. And this is the idea of substitution, just like what I've been doing up here, right? Where we say, we've got a du dx, come on down to here, du dx times dx, well, that's equal to du. And then we work from there. So, to look at what they've done, they declared u to be equal to 1 minus 3x. If that's the case, then du dx is going to be equal to -3, and du is going to be -3 dx. Okay. So now we come through here and we say, cool, I can multiply by -3 and divide by -3 and get out my du dx. And then reduce the math. We have a couple general guidelines. This is on slide 55 in week 10 notes. You can find those under exam 4 on Blackboard. This is just a general set of rules for how to solve these problems. It has a couple notes on this. If you go online and start Googling around on how to solve these types of problems, just for like your own personal better understanding, right? To understanding beyond what I've been able to explain in class, you're going to find a lot of stuff on U sub. That is exactly what we're doing here. It's a method called U substitution. You're just rewriting your integrand in terms of U, and then your differential in terms of du. And the way all this works is we use the chain rule. You say, cool, if we have a function that is a composition of f with some u of x, so our exterior function and our interior function, the derivative of this thing, it's just going to be the derivative of f with u as our input, right? Times the derivative of u with respect to x, just like we talked about before. So the integral then of just a general function, let's say we have some function with respect to x, g, and we differentiate it with respect to x, well then you're gonna get this sort of cancellation. Like I said, it's not really a cancellation, but you can think of it as sort of like one. That reduces this to just d of g, the integral with respect to g. But g is a function of x, so what you're going to get out is g of x plus c. That same set of thoughts applies here. These differentials can be thought of as canceling, so that reduces your exterior function to just a function of your interior function, which can be thought of as the variable u. You're integrating now with respect to that variable. One way that I oftentimes will like to write out these problems and solve them is just set up the integration initially, right? And rewrite everything so that my du dx is sitting next to my dx. Dx always has to be on the outside, right? We'll say, all right, cool, I've got my u, this is u cubed, which, there's a typo here, this should be u cubed. And I know that u is equal to x squared plus 3, so du dx is going to be 2x, that's why I wrote it this way, right? So if du dx is equal to 2x, then du dx times dx is going to be 2x times dx. I'm going to say this is equal to du. So now, using these substitutions, I've got f of u is equal to u cubed. I've got u is equal to x squared plus 3. So I can replace this with u to get f of u. And then I can say du dx, well, that's equal to du, but 2x dx is what du dx represents. So I can replace this with du. Once I do that, I get the integration of u cubed with respect to u. That's equal to 1 over 4 u to the 4th plus c. But now I've got this, but I know that u is actually equal to x squared plus 3. So I substitute that back in. Now, to do that in practice. Do that in practice, what we've got. Start off with this integral, x times the quantity x squared minus 1, all raised to the 1/2 power, dx. And I'm going to sit here, I'm going to say, let's try to set u equal to x squared minus 1. If we do that, then du dx is going to be equal to 2x. And if that's the case, then du dx times dx is going to be equal to 2x dx. Well, I don't have a 2 here, but I can force a 2 to show up, right? Multiply by 1/2, divide by, or multiply by 1/2 and 2, right? So what I'm saying is we can rewrite now x times the quantity x squared minus 1 raised to the 1/2 dx. And rewrite this as 1/2 times 2x times the quantity x squared minus 1 raised to the 1/2 dx. Hey, check it out. We've got du right here. And we've got u right here. So I can rearrange all of this to get 1/2 the integral of x squared minus 1, all that raised to the 1/2 power, right? times 2x dx. But when we do that, this thing becomes du, and this thing is u. So I could rewrite this integral as, let me put it over here. I could rewrite the integral x times the quantity x squared minus 1/2, or minus 1 raised to the 1/2 dx. By substitution, u is equal to x squared minus 1. So du is equal to 2x dx. We could rewrite this integrand using this substitution as 1/2 u raised to the 1/2 du. This is easily solvable. 1/2 the integral of u to the 1/2 du is equal to 1/2 2/3 u to the 3/2 plus a constant. So this comes out to be 1/3 u to the 3/2 plus c. And when we substitute back in, u is equal to x squared minus 1. We get 1/3 the quantity x squared minus 1 raised to the 3/2 plus a constant. And now checking our work really quick. We start off by defining what u is and finding what du is then. If u is x squared minus 1, then du dx is going to be just 2x. So du is going to be 2x dx. That's what we got right here. Now, rearranging everything and identifying how all this works together, we've got u, we've got du. We can use the substitution to get this nicer integral that we know how to work. From that, we solve that integral. Then we just substitute back in what u was. It was x squared minus 1. And we can check just by differentiating our answer. And just to show what that does, once you differentiate, this goes to 0, right? It's constant. We're going to get 1/3 times 3/2. So we're going to have a cancellation here to get 1/2. Then we're going to have a 2x come out, right? When we simplify all of this, we get exactly what we started off with. So as a way of checking your work, differentiate your answer. It's always a good place to go. For the sake of time, I'm going to go ahead and jump into section 5.3. Actually, I'm going to say let's take a 5-minute break. Come back at, okay, 7-minute break. Come back at 8:15.